Last class we would have looked at waves. We looked at the interference of waves. Previously we also looked at electromagnetic waves. I asked you all to do a little bit of reading on the different rival theories of light. There were some theories that suggested that light behaves like a wave, and some theories that suggest that light behaves like a particle. So we are going to look at those theories and we will see where it leads us to today. At the beginning of the 18th century, there were two rival classical theories on the nature of light. The wave theory, which means that light behaves like a wave, and the corpuscular or particle theory, meaning that light behaves like a particle. So let's look at the first early contributions of the wave theory. So in 1690, Huygens suggested that light was a longitudinal wave, right, capable of propagating through a material called ether, right? So what he believed is that everything here that we call space, right, is made up of invisible matter known as ether, right? So he's saying that along this wavefront, in order for you to receive the second wavefront here, there are tiny points along the wavefront, right? And those points create circular waves. And these circular waves will form a secondary wavefront. And then with those make a wave, then you will have another set of wavelets that will be forming a third wave, and that is what will cause the wave to propagate. Alright, so if you read through that, that is what he's talking about. The advancing wavefront is therefore always perpendicular to the direction of propagation of the wave. Then Newton came along in 1704 and he thought that light behaves like a particle. He said that light was shot out from a source as particles, and he believed that the mass of the source diminished as it released those particles. So at the time, there was no observation of the diffraction of light, right? They did not come about how to observe the diffraction of light. And he argued that since light cannot be diffracted, then it cannot be a wave. It must be a particle, because remember, diffraction is one of those properties of waves. Also at that time, it was not known that light travels faster than air in water. So Newton's theory suggested that it should be faster in water. Right? So there were a lot of things to debunk his theory. His argument could not explain, however, why the velocity of light was not higher when coming from bodies of higher temperature. Now, why should that matter? Right? If we think about it, if it is a particle, remember, if light is to behave like a particle, then the more energy that light is given, then that particle should be vibrating faster, right? Because that particle should gain kinetic energy. So it should have meant that bodies which are higher in temperature or are hotter to the touch, then they should have a faster speed, right? Because the particles themselves will have more kinetic energy. Then Young came along. So Young showed experimentally in 1802 that light from two very narrow slits can produce a pattern of bright and dark fringes on a screen. So I started to explain something similar to this when we were looking at the interference of waves. So we looked at how waves can interfere, and we will have alternating periods where we will have maximum amplitude, and then we will have, if we are talking about light, we would have had bright and dark fringes, right? So Young's double slit experiment, which was one of the experiments you had to research on, is what helped to prove these theories. So he showed experimentally that if we have two coherent sources of light passing through, right? So if we want two coherent sources, remember we can use one source of light and a screen in front of it with two narrow slits to mimic two separate point sources, right? And a pattern of bright and dark fringes was seen on the screen. So we will look back at that pattern in a little bit. He argued that this was the result of the principle of superposition of light acting as waves, right? Because particles cannot do that. However, Newton's corpuscular theory still lived on, mainly due to his reputation as a dominant physicist and mathematician. Wave theory by Foucault. So Foucault showed experimentally in the 1850s that light traveled faster in air than in water, right? Now remember, previously Newton would have said that light travels faster in water, right? Contrary to what Newton's corpuscular theory suggested. This seemed at the time to be a deciding factor that tilted the balance in favor of the wave nature of light. So slowly, the particle theory began getting debunked, and wave theory, so meaning that light is a wave, that started to take over. What really happened in the end is that light is very magnificent, right? So Planck and Einstein, Max Planck in 1990 put forward what is known as the quantum theory. If you'll ever heard about quantum physics, that is based on quantum theory, which combined the wave and particle theories. So these two brilliant scientists did something unbelievable. So in 1905, Einstein showed that the phenomenon of the photoelectric emission, or what is known as the photoelectric effect, cannot be explained by the wave theory, but only by the particle theory. On the other hand, the particle theory could not explain phenomena such as diffraction and interference. Because if we think about particles, how are they going to diffract? How are particles going to interfere? Which were clearly due to waves. Einstein had also shown that there is an equivalence between matter and energy in accordance with his famous equation E equal mc squared. I am sure you all would have noticed a little diagram behind me when I am teaching live, right? I have a poster of Einstein and there is that equation on it. E equal mc squared. So they have it listed here as delta E equals delta mc squared, meaning that the change in energy is equal to the change of mass times the speed squared, right? So this was a very important equation. Today we accept the quantum theory, which considers light as a particle as well as a wave. Each wave pulse is a packet of particle energy known as a photon. So you would have heard about photons. When we talk about light, you would have heard that term photons, right? So in reality, it worked out that light behaves both as a particle and as a wave. So light is very unique in that wave theory alone could not describe some of the things that light can do, and the particle theory alone could not describe some of the things that can do. So in the end, at this point where we are at, we don't know if in the future they might figure out more stuff and decide that maybe light is something totally new. It's a theory that was never discussed before. So we never know. But for now, we are looking at light as having that duality. So it is known as the wave-particle duality of light. We already looked at diffraction and interference. So these notes are from the Collins Concise course. So you all can read through these extra stuff from the Collins, right? Because I would have given you all notes from the Physics for CSEC book. Alright, so all of these would have been things that we would have done already. We talked about coherence, so I just want to kind of close off some of the things about waves in general, so that when we are ready to move on to the next topic, we have more or less covered all our bases. So vibrations are known as coherent if they are in phase or they have a constant phase difference. They must therefore have the same frequency. Alright, so you could make sure and read that. And in order for us to see the interference of light or the interference of waves, we would have needed sources that were coherent. The waves produced must have the same amplitude and shape. Right, so we discussed that for Young's, well, this here is Young's double slit experiment, right, that you were supposed to look up at. So we're going to go through this very slowly so that you all can see the bright and dark fringes. It was very similar to when we looked at the interference patterns of water waves in the ripple tank. So before we get to that, I just want to recap a little bit of light waves. Right, so light is really just like electromagnetic waves, and they are transverse waves, so they are not longitudinal. Light is a form of energy, and because it's a form of energy, it can be conceptualized to be transported in two ways. So light can behave like a particle, so it can move like a particle, or it can have a wave-like nature. When we think about light as a particle, it can demonstrate reflection and refraction. And if we look at it as a wave, we will see that it can diffract and interfere. Right, so we looked at the different theories. So we looked at the first theory, which was developed by Huygens, and that was later debunked. Right, so it eventually, Thomas Young was able to conduct this experiment known as Young's double slit experiment, and he was able to prove that light is behaving like a wave because of those dark and bright interference patterns. Right, because if light was just a particle alone, then it should not have been able to observe diffraction and interference. So that is why we have come up with that light behaves as both. It can behave as a particle or it can behave as a wave. Right, so we are going to look at Young's double slit experiment. And what he realized is that the size of the slit, just like when we looked at water waves, it must be similar or comparable to the wavelength of your source of light. Right, if the slit is too wide, the interference pattern is not going to be strong, because when the wave diffracts, remember, it's only going to diffract a little bit on the ends. So you want to have maximum diffraction happening. So you want that nice curved wavefront happening when it passes through the slits. So you want to make sure that the slits are very narrow, right? So the slits must be similar in size or smaller than the actual wavelength of your source of light. All right, so let's look at Young's double slit experiment. So he has a monochromatic source of light, meaning that it is one color of light, right? Because remember, the different colors of light, they have different wavelengths. So you want to just have one color, right? And we are going to diffract it through two narrow slits. So one source of light, and then we're going to have this screen here. This is a screen with two narrow slits, and what that will do is create two point sources of light that are identical in nature, right? So we will have two coherent sources. So that is very important to note. So these two sources here, these are two coherent sources. So make sure and take note of that. If they were not coherent, we will not be able to observe the interference pattern properly. And then undergoing further diffraction through two other narrow slits, S1 and S2. So they are separated roughly about 0.5 millimeters apart. So very close together. It's a very small setup. The emerging wave fronts progress towards a translucent screen, right? So this is a translucent screen here, where they superimpose and form an interference pattern. So this region here, if we look at this, that is one source of light spreading out as it comes through the slit. So that is that one source of light diffracting as it comes out. If I use a different color, you are able to see this here is the second source of light. Right, so I did not draw it exact, but this here is your second source of light. Right, so remember when we looked at it, right, we would have said that where you have two crests coming together, you would expect maximum amplitude. In terms of light, you will expect a bright fringe. Right, so what you will see is an interference pattern of bright and dark fringes. It must be performed in a poorly lit room so that you can observe the interference patterns. If the place is too bright, you are not going to be able to see it. So you have to make sure that the size of the gap is not larger than about 10 to the minus 7. You're looking at very, very small amounts, right? So what will happen as the light diffracts through each of these slits, the diffracted beams are going to interfere with each other. So in the middle here, we are having interference happening, right? So when the two sets of waves interfere with each other, as we said before, you are going to have bright and dark fringes. Where you have a bright fringe, this is where constructive interference took place. And where we have a dark fringe, this is where destructive interference took place. Alright, so I do apologize for that. My page just skipped ahead. I'm going to get it back. Okay, good. All right. Now, in the middle, we are going to have the brightest fringe. And then it's going to be bounded by two dark fringes. All right. And then you will have another bright fringe on either side. And then you will have another dark fringe and so on. It is very important to note that the distance between two consecutive bright fringes is going to be lambda, or the wavelength, right? So it's very important. And similarly, the distance between two consecutive dark fringes is also going to be the wavelength. So it's very easy to see that. So that little experiment there showed us that light does in fact undergo diffraction and it undergoes interference. Right, so here they have some of these things that you can use as a monochromatic source. So you can use a sodium vapor lamp, so that will only show yellow light, which is a monochromatic source, one color of light. Alternatively, a filament lamp can be used, which is emitting white light, but you will have to place a filter in front of it so that only one color will pass through. Right, and as I was explaining before, you cannot use just regular light, because if you don't use the filter, all of them have different frequencies. So because they have different frequencies, they will be constantly overlapping each other, and you are not going to observe that interference pattern. All right, So I also explained how S1 and S2 would be coherent sources by using that screen with two slits in it, right? So let's read over bright fringes and dark fringes. That's the same thing I was explaining just before. So when the waves from slit 1 and slit 2 meet the screen in phase, their path difference is a whole number of wavelengths, right? So they undergo constructive interference resulting in a bright fringe. So between every two bright fringes, it's going to be a distance of lambda, right? And that lambda is the wavelength of your light. Similarly, for dark fringes, when the waves from S1 and S2 meet, the screen is exactly out of phase. So their path difference is half lambda, or half of a wavelength. So that is where you will expect them to be, right? So this is going to be half of a lambda on either side. But the distance between two consecutive dark fringes is also going to be lambda, or one wavelength. So if you are shown a diagram with interference patterns and you are asked to calculate the wavelength, then you can simply measure this distance here, and that is going to be the wavelength of your source. Young's double slit experiment provides the evidence for the wave nature of light, since interference can only happen in waves, right? So interference is known as a wave phenomena. Young's experiment in relation to sound waves. So when we did sound waves way back last term, we would have looked at interference in sounds, right, in terms of having that loudness or the amplitude being maximum. Right, so we would have already covered shadows and eclipses, the pinhole camera. We looked at reflection and refraction. We also looked at the refractive index, and we looked at the dispersion of light. We looked at critical angle and total internal reflection. And I ask you all as well to look at some of the applications of total internal reflection. So we have to do lenses, but before we get to lenses, there is a little bit of waves that we did not complete, which was real and apparent. On page 94 of the Collins textbook, there is the example of what will happen when sound waves interfere. So sound waves can interfere. Same thing like when we looked at light waves and water waves. In order to observe interference of sound waves, you need to have two coherent sources. So this is how the experiment can be done. So a signal generator connected to a loudspeaker as shown emits a note of constant frequency. Speakers S1 and S2 are coherent sources, meaning that they would emit waves in phase or with some constant phase difference, right? So if they have a constant phase difference, we are expecting, all right, this is just a little example, right? So let's say those are the wave fronts, right? I'm gonna try to do some wave fronts here as well, right? So we would have had a bunch of wave fronts like this after the diffraction, right? So you'll expect them to interfere. They will have points where two crests would meet, right? And then you will have points where a crest and a trough meets. So if somebody, eventually what will happen here, just like how we had bright and dark fringes, we will have places where you will be hearing this sound extremely loud, which will be where you have constructive interference, right? And then you will have places where you will hear no sound, and that is where you would have had destructive interference occurring. So an experimenter walking along the line AB will observe alternate points where he or she would hear no sound and then a loud sound. Where the waves from S1 and S2 meet the experimenter in phase, you will have constructive interference happening, right? And wherever constructive interference happening, that is where you will get the loud sound. And wherever you had destructive interference happening, you would get no sound because they will cancel out each other. Right? So nothing would be heard. So sound waves will therefore exhibit the phenomena of interference. Right? So we would have looked at interference of waves in the ripple tank. So that would have shown that water waves can experience interference. We would have also looked at Young's double slit experiment, showing that light in fact does interfere. All right, and then the last one was sound waves, and they also observe interference. And for all three of them, in order to observe the interference patterns, you must be using coherent sources of the wave. Right, so a little bit to tie up some of the stuff that we did on light is that light can travel whether there is a vacuum or not. Light will travel at a constant speed in air, which is 3 by 10 to the power 8 meters per second. Light can undergo reflection, it can undergo refraction, it can undergo diffraction, and it can also undergo interference. Light can behave as a particle, and light can also behave as a wave. Another important concept of light is that light travels in straight lines. And when we looked at the pinhole camera and solar and lunar eclipses, that would have shown us evidence that light does in fact travel at straight lines in order to see the formations of those shadows and in order to create the image in a pinhole camera.